So we have two stereo speakers mounted 4.52 meters apart on a wall. They're emitting identical sound waves. That's important to know because that tells us that the delta phi naught is 0. We're standing at the opposite wall of the room at a point directly between the two speakers. We're going to walk 2.11 meters parallel to the wall to a location where you first notice that the sound intensity is much less. If the wall along which you are walking is 13.3 meters from the wall with the speakers, what is the wavelength of the sound waves? So it'd be like having two speakers on the wall, one here and one 4.52 meters over there, and then more on the back wall. So if we were looking down into our room here, we have a speaker here and a speaker here. They're 4.52 meters apart. We're directly across the room, and we start out at a point halfway between the two speakers. This distance is 13.3 meters. Right here, we're equal distance from both speakers, so that would be a point of perfect constructive interference. Both waves are in phase when they leave the speakers, which is what is meant by identical sound waves. If they travel exactly the same distance, then they will still be in phase when they reach us, and we will have perfect constructive interference. So we start walking. It doesn't matter if we walk to the right or to the left, but we walk 2.11 meters. So we're now here. This is the first point. We notice that the sound intensity is much less. So we're hearing a point of perfect destructive interference. So from that information, we need to determine what the wavelength of these sound waves are. So destructive interference. If delta phi naught is 0, the equation we derived for delta x being the extra distance that one wave travels compared to the other, the equation we derived was this. Delta x was equal to some multiple of half a wavelength. We're first noticing that the sound intensity is less. So this is the first point of perfect destructive interference. So what m value do we want?
1. 0.
So the first point of destructive interference means the smallest possible value of m, and m can be 0. So this means the extra distance one wave traveled versus the other is exactly 1/2 of a wavelength. So the wavelength will be exactly twice that extra distance. So we need to find the extra distance. We need to know how far this wave traveled to get there. Call that x1. We need to know how far that wave traveled to get there. We'll call that x2. You can make a right triangle right here. We know this side is 13.3 meters. This side will be half of the 4.52 plus the 2.11. So this side's 4.37. So Pythagorean theorem I get 13.9995, so more or less 14 meters. This one, we could do a right triangle as well. Can come straight down. This side's 13.3 meters. This side is the 4.52 meters divided by 2 minus the 2.11.
You just say 4.52 minus 4.37.
Or that, yes. That works great too. So 4.52 minus the 4.37 also works. So this side is 0.15. So Pythagorean theorem again, 13.3 squared plus 2.3 is basically 13.3. So delta x,
0.7.
right? So 0.7 meters. So the wavelength of these sound waves is 1.4 meters long. We could easily find the frequency as well, because we know the speed of sound. So the speed of sound over the 1.4, if we wanted the frequency, it would be 245 hertz. Wasn't asked for, but easy to find. Any questions on that?
Just real quick, how did you find the frequency?
Frequency, remember, is speed over wavelength.
Or the relationship is velocity equals frequency times.
Right. And since we know it's a sound wave, it travels at 343 meters per second, we just found the wavelength.